All right, everybody. Here we are, third part in our discussion on sequences. We're introducing these things. We've done some calculus, some limits in the last one. Now we need to chat about a couple of ideas to wrap things up. Another way to evaluate the limit of a sequence is with the squeeze theorem. So you might remember that way back from when you first learned limits in Calc 1. Well, we've got this exactly the same idea, but now for sequences instead of functions. So here it is in the official definition. If the limit as n approaches infinity for a sub n is equal to the limit as n approaches infinity for another sequence b sub n, and those maybe we say that they both equal L, and there exists capital N such that a sub n is less than or equal to c sub n, which is less than or equal to b sub n, for little n greater than capital N, then the limit as little n approaches infinity for c sub n, well, that has to equal L as well. So some very technical language, really making it a lot more confusing than it needs to be. If you remember the squeeze theorem from Calc 1, then that's great. Maybe here a drawing is helpful, and you see I kind of noted to myself, maybe I want to skip this if this was in the lecture. I think I'll just show it to you guys here. I won't skip it. It's kind of my note to myself there. Should I skip that? So if you can even follow what's going on, I know it's pretty blurry, but okay, so kind of right here we've got the A1, A2, A3. Down here we've got B1, B2, B3. At some point we need that capital N. Capital N is a value of little n. So there's AN, BN, and then we've got the C's coming down. So at first C1, C2 is out here, but then eventually C3 sneaks in between. And what we're saying is that from this point onwards, at a minimum, the C is captured between A and B. That's that statement right here. A sub n less than or equal to C less than or equal to B for n greater than or greater than capital N. So as soon as we hit capital N, now we know C is in between them. Actually, I think I've reversed the positions of A and B. The A should be at the bottom, the B should be at the top, but you get the idea. Okay, well, if we know that the limit for the A and the limit for the B, if those are the same, they're both equaling L, then the limit for the C has to be the same thing if it's caught in between. Okay. Hopefully that makes sense. How does it apply? So we'll see it applied to maybe some trig. That was the case back in Calc 1, if you recall. What if we've got A sub n? Our sequence is the sine of n over n. And so we think of sine of n like a continuous function, but maybe we just plug in n equals 1 equals 2, right? That sort of thing. So we know to use the squeeze theorem, or at least I'll tell you that. We begin by saying, hey, I know that the sine of n, whatever the value of n, is always somewhere between -1 and +1. And I'm going to use that fact to create my sequence. If I divide all three of them by n, right, then I can say that sine of n divided by n is caught between -1 over n and +1 over n. Just based on the previous line, if I divide all three by n, I would get this statement. Okay, so what I'm going to do now is I'm going to look at the limit on, maybe I can do something like this, the limit on the left side and the limit on the right side as n approaches infinity. Well, if I take the limit of this guy, I know what that one is. If I take the limit of that one, I know this. So the limits on the outer ones are closing in on 0. So what does that mean for the inner piece as n goes to infinity? Well, I can just say it. That limit's going to 0 as well. And so the answer here in part F is that this limit converges to 0, or this sequence, I should say. Okay? Okay. So that was the last of our sequence examples. Now just some terminology to wrap things up. Again, sorry this is so blurry. I don't know. It's crystal clear here on the paper. So that says, if you can read that, well, that's a little bit better if I lift it up. It says monotonically increasing. So we've got this new language for sequences, monotonic. So something is monotonically increasing if the terms are never getting smaller. So we see that the terms might be equal as we move along, but they're never getting smaller. And they could get bigger as well, of course. Maybe you say they're not decreasing. That's what monotonically increasing means. Always getting bigger or the same. We can define monotonically decreasing, right? Similarly. The values might be equal or they might be getting smaller as we move out. They're non-increasing, okay? We've got this language for being bounded. Maybe a sequence is bounded above. There exists capital M such that all of the terms of the sequence are less than or equal to capital M for all n, right? Every term is less than or equal to that. Then it's bounded above. We can have bounded below. There exists capital M such that every term in the sequence is greater than or equal to capital M. Capital M is a lower bound if every term is bigger than or equal to it. And then these two ideas of monotonic and bounded can come together. We're going to finish off the section with this theorem. If a sequence is monotonic and appropriately bounded, then it converges. So appropriately meaning if you are monotonically increasing, right, maybe you're always going up, and you've got an upper bound, then you must converge. And you likely converge to that upper bound. And so I've drawn a picture of that here. So I just kind of drew some random terms. They're always either equal or getting bigger, each value in the sequence. And there's this upper bound. So as you go up and up and up, well, you're going to have to converge probably to what that upper bound is. It could be the same if your terms were monotonically decreasing and you had a lower bound. Then we know that that sequence would converge as well. So you'll get a couple of questions on monotonic and boundedness in the homework. Really just want you to be familiar with that language as it might come up later in the chapter or in a future course. That's it for this section. So we're also going to put up 11.2 because we were going to cover that on the same day. So that will be up as well. Okay, good luck with your homework, and I'll see you in our class session.